Hey guys, welcome back to another A-Level Maths revision video. And in this video today, we're going to take a look at the final predicted paper, paper 3 on stats and mechanics. So this is the applied paper, which is the final paper you sit. Before we start this paper, I just want to make a quick point, and that is in relation to the large data set. So I've removed any references to the large data set. And the reason why I've done that is because it differs between exam boards. And I essentially want this video and this paper to be accessible to students of any exam board, so it serves as good revision. And removing the large data set, I think, is the best way to accomplish that. So there's no references to the large data set within this paper. Everything is just the stats and mechanics, no large data set. Okay, like always, the questions are taken from the topic tests, a couple of questions from the new papers, but not too many, and then the old M1, M2, and S1 past paper questions. Okay. So I think that concludes everything I wanted to say. So let's jump straight into this predicted paper. Starting with question 1 here on this predicted paper, we're beginning with the stats part to the exam. So everyone's favourite, part A, pretty straightforward. So what we've got here in context is the heights, x meters of 40 children. And then we've got these summary statistics here. So in part A, we're just simply asked to find the mean and the variance of the heights of these 40 children. So for the mean here, because we're looking at a sample, this will be x bar, the sample mean, so x bar. And the formulas are in the formula book, like we said, but I'd say they're pretty straightforward to remember. So for the sample mean here, x bar, that's just sigma x divided by n. Okay, so sigma x we know, that's given to us here, so that's 58. And for n, remember n is just the sample size. So we're told we have a sample of 40 children. It doesn't explicitly say the sample, but that's what we're looking at. We're looking at a sample here of 40 children. So we divide this by 40. So we do 58 divided by 40, put that into your calculator, and what you should get here is 1.45 there. Okay, so that's the mean. We now need the variance of these heights, so we write this as s squared. And it's a pretty similar formula, and you should always start with the mean. I'll calculate the mean first, and the reason for that is because you need the mean to calculate the variance. So for the variance here, that's going to be sigma x squared. We divide that by n, and now we minus x bar squared. So we minus the mean squared. So minus x bar squared. So sigma x squared we're given as well. So that's 84.829. We divide it by n again, which we know is 40. And now we minus the mean squared. So minus 1.45 squared. And again, just put this into the calculator to see what you get. And what you should find here is you get 0.018225. And if we give that, say, to 3 significant figures here, and we're going to get 0.0182 there. Okay, so that's our variance there. So that's part A done. For part B now, we're told the teacher decided that these statistics would be more useful in centimetres. So the first part here is asking for the mean of these heights in centimetres. So we worked out the mean here, but this was for metres. Okay, so the mean height here is 1.45 metres. So if we want the height in centimetres, or the mean height in centimetres, we just need to think about how we convert from a metre to a centimetre. And in that case, we know that 1 metre is simply 100 centimetres. So hopefully you are familiar with that if you're doing A-level maths. So 1 metre, 100 centimetres. So in that case then, if we know the mean height here was 1.45 metres, then we just need to times this by 100. That would give us our result in centimetres. So in that case, the mean height here in centimetres will be 1.45 times by 100, which gives us 145 centimetres there. So that's the mean height in centimetres. And clearly your answer should make sense. If you get something like 14.5, that's very, very small. That's less than a standard ruler. So clearly that's not the mean height. And if you get, say, 1,450, again, that's ridiculous. Something's gone wrong as well. So always double check that your answer makes sense. So that's the mean heights in centimetres. We now want the standard deviation of these heights in centimetres. Now, be very careful here. This was for the variance. Okay, these results here. This was the variance. But we want the standard deviation, so just be very, very careful. Remember, for the standard deviation, this is equal to the square root of the variance. So let's just write that down here. So the standard deviation is equal to the square root of the variance, okay, the square root of var. So the standard deviation here in centimetres, that's going to be the square root of the variance, but remember we want this in centimetres now, so again we just need to times this result here by 100. Okay, make sure you use this part here as well, the unrounded figure, because we're going to take the square root here. So we're going to do 0.018225, and then we times that by 100. Okay, again, like always, put this into your calculator, and what you should get here for the standard deviation is 13.5 there. Okay, so that's the standard deviation of the heights in centimetres. So that's part B done for 2 marks, and we arrive at part C now. So let's just clear the screen just so we've got enough room for part C. So we're told here that 2 more children joined the group. Their heights are 130 centimetres and 160 centimetres. So for the first part, we're just asked to state, given a reason, the mean height of these 42 children. So part C, or C here, part 1. So the new heights are 130 centimetres and 160 centimetres. So what would happen here? Well, if you think about it, adding these 2 extra heights in, all we need to consider is what's the average of these 2 individual heights. Because, for example, if the average of these 2 heights is 145, just like we've worked out here for the heights in centimetres, then it wouldn't actually affect the mean height of the 42 children. It would just remain the same. So in that case, let's work out the average of these 2 numbers. So we're going to do 130 plus 160, and then we're going to divide that by 2. So that's going to give us 290 over 2, which would give us 145, which is perfect. Because what that tells us then is that the mean of these 2 children is 145. So when we add those on to the original 40 children, the mean won't change. It will remain the same. Another way you could test this would be to write these as meters. So that would be 1.3, that would be 1.6. Add them on to sigma x, divide by n that way as well. You can do that, but this way, hopefully you can see the intuition behind it. It saves you a bit of time calculating this part here with sigma x. So because this is 145, what we can say here is the mean won't change. So the mean won't change. As the mean height of the 2 new children. So the mean height of the 2 new children is also 145. Okay, so that's all we need to say there for part 1 for C. For part 2, this is a little bit trickier, conceptually anyway, to understand. So this says now, without recalculating the standard deviation, state, given a reason, whether the standard deviation of the heights of the 42 children will be greater than, less than, or the same as the standard deviation of the heights of the original group of 40 children. So, where do we begin with this? Well, what we do here is let's just think about this on a number line, essentially. So I'm going to do a very rough sketch. Now, we know our mean height here was 145 centimetres. Now, if you think about this, what we're going to do here is consider this between 1 standard deviation. So we know our standard deviation, that was 13.5. So that was 13.5. Okay, so we've got this in centimetres here. We'll use the standard deviation in centimetres. Now, if we take 13.5 off 145, that would give me 131.5. And if I add 13.5 to 145, that would give me 158.5. Okay. Now, what we're saying is, if this was the mean, the heights of these 2 children, so if the children were 131.5 centimetres rather than 130, and they were 158.5, what would actually happen here? So let's just say that's where they are. So they're there and they're there. The standard deviation would remain exactly the same. And the reason for that is because they lie exactly one standard deviation away from the mean. Okay, so that's one standard deviation, same here. Okay, so because they lie exactly on this point here, then it wouldn't change the standard deviation for the 42 children. Now, if they're within, so let's just use a different colour to illustrate this. So let's say they're within this area here, same here, then the standard deviation will be smaller. Essentially, the spread of data is getting smaller, so the standard deviation will decrease. And if they're greater than one standard deviation, so if they're outside, so again, let's just shade this with a different pen colour. So if they're outside here, so a value less than 131.5 and a value greater than 158.5, then because the data is getting larger, the data spread is getting larger, then the standard deviation will increase. Okay, so if we think about our two values here, we've got 130. So again, I use one more pen colour just to illustrate this. We've already used that one. Let's try green. So we've got 130 centimetres and 160. So 130 might be, say, here. That's our child 1, say. And then we've got 160 centimetres, which let's say is there. Okay, so that's 160. That was 130. So because these are greater than one standard deviation away from the mean, what that means then is, like we just said, the spread of the data is getting larger, so therefore the standard deviation will increase. So all we need to do is just summarise that. So the standard deviation will increase. So the standard deviation will increase. And just to save time, I won't give the final line, but I'll kind of read out what I'd say here. So all I'd say then is the extra children are greater than one standard deviation from the mean. So we have increased spread, and as a result, the standard deviation will increase. Okay, so like we said, hopefully this diagram kind of illustrates that. So remember, we were looking at one standard deviation from the mean, where the standard deviation here is 13.5. So all I did was subtract 13.5 off 145 and added it. So that was adding it, that was subtracting it there. And like I said then, if it's greater than that, it's going to increase. If it's less than that, it would, the standard deviation would decrease. And if it was exactly 131.5 and exactly 158.5, then that's when it would not change. Okay? So there we have it. So that's part C done, and that gives us the solution there to question 1. Moving on to question 2 now, we have a question here on probability and Venn diagrams. Now question 2 is split up into quite a few parts, so before we start with part A, let's just read the question carefully and see what we're dealing with. So it says an integer is selected at random from the integers 1 to 50 inclusive. So A is the event that the integer selected is prime, B is the event that the integer selected ends in a 3, and C is the event that the integer selected is greater than 20. And the Venn diagram shows a number of integers in each region for the events A, B, and C. So for part A, just 1 mark, we're asked to describe the event that's given here. So you need to be familiar with this notation here. So hopefully you're familiar with this. This is what we call the intersection. So this is the event of A intersection B. Okay, so this is A intersection B. And the way we think about this with the intersection notation is this is A and B. Okay, so this is A and B. So A is the event that the integer selected is prime. B is the event that the integer selected ends in a 3. So in that case, if we want A and B, this event here, well, in that case, what this tells us then is we're looking at an integer that is prime and also ends in a 3. Okay, so that's important, the and part there. So we're looking at for, essentially here, if I can word it correctly, an integer that is prime. So an integer that is prime, or is a prime number, and ends in a 3. I'm terrible at English, you can probably word it better than me, but hopefully that makes sense. So ends in a 3. Okay, so we're selecting an integer that is a prime number and ends in a 3. Okay, so it's and rather than or, because we're using intersection notation. So that's part A, that's all we need to really say for 1 mark there. For part B, we're asked to write down the probability that the integer selected is prime. So to determine this probability, we need to just take a look at the events here. So A, B, and C. And we're looking for which event is taking a look at integers that are prime. And in that case, we're looking for event A here. Okay, so A is the event that the integer selected is prime. So all we need to do then is look at this circle here for A, and we're looking for all the integers inside, or the number of integers inside this circle. So we've got 6 integers there, 2, 2, and 5. So all we need to do is add all of those numbers together. So that's going to be 6 plus 2 plus 2 plus 5. And obviously we need to do this out of the total number of integers for this Venn diagram. So because we're looking at the integers from 1 to 50 inclusive, this will be out of 50. So this is going to be divided by 50. Okay. So all we need to do now is simplify the numerator here. So 6 plus 2 is 8, plus another 2 is 10, plus the 5 gives us 15 over 50 there. Okay. So that's all we need to do for part B. For part C then, it is only 1 mark, and it might look a little bit trickier based on the notation here than it needs to. So let's have a look at this. So this is the probability of A, and again, just being familiar with the notation here, this like U shape, this is what we call the union. So this is A union B union C, and then again, just more notation here. This little mark here, this is what we call the complement. So this is the complement. So what's this asking us for? Well, if we start here with the square bracket, so this is A union B union C. So this is A or B or C. So in other words, it's everything within all 3 circles here. But because we then take the complement of this square bracket, that means everything outside of these circles. Basically anything that's not in these circles. So in that case, we're looking for everything on the outside here. Just to highlight what we're looking for. Well, in that case, that would just be this 12 here. Okay, so that means there's 12 integers outside. So the probability then is going to be 12 out of the total number of integers here, which, like we already deduced in part B, is 50. So that's going to be 12 out of 50 there. Okay, and that's all we need for part C. Like you see, it's only 1 mark. Not too much work. It's just mainly testing that you're confident with the notation. So yeah, so that's all we need for part C. So let's take a look at part D now. Now part D, 2 marks. This is where we start getting into slightly more complicated material. It's nothing too crazy, but we're now looking at conditional probability. So because we see this word here, given, as soon as you see that with a probability question, you should be, aware that we're going to use conditional probability. So the question says, given that the integer selected is greater than 20, we want to find the probability that it's prime. So what we're conditioning on here is this here. So we're conditioning on the fact that it's greater than 20. So if we just refer back to the events here, C is the event that the integer selected is greater than 20. So what we're looking for is a probability. So this is going to be the probability of some event here, which we won't define just yet, but we're conditioning that on the fact that it's going to be greater than 20, which we've just said is the event C here. Okay, so we're conditioning that on C, or given that C here. So what's the first part going to be? Well, we're looking for the probability that it's a prime number. And if we just refer back to the events again, in that case, that must be A. So A is the event that the integer selected is prime. So that's going to be the probability of A given C, okay, or A conditioned on C. Now, for this part here, all we need to do is use our conditional probability formula. So remember, if we're looking for the probability of A given C, this will be the probability of A intersection C all over the probability of C. Okay, so what I need to do now is calculate each one of these individually. So the probability of A intersection C, so A and C, well, we just look at our circles here and look for where A and C are intersecting, and what we get then is 5 here and 2 there. Okay, so that gives us 7, but this is a probability, so what's it going to be out of in total? Well, that's going to be out of 50, so we get 7 over 50 there. And for the probability of C, well, in that case, this is going to be quite straightforward. That's just everything within the circle of C. Okay, so 5, 2, 1, and 22. So 27, 29, 30. So that's 30 over 50. Okay, so just about got enough room there. So all we need to do then is substitute these two values here into our formula. So the numerator, that's this 7 over 50. So 7 over 50. And then we divide this by the probability of C, which is 30 over 50. So we divide that by 30 over 50. And here, this cancels quite nicely. The 50s just cancel, and I get left with 7 over 30 there. Okay, so that's the probability of A given C. Or as the question asks for it, the probability, or given that the integer selected is greater than 20, find the probability that is prime. Okay, so that's how we mathematically define that with the correct notation. So that's part D. Part E now, it says using your answers to B and D. So this figure here, and at some point something in D here, we need to state with a reason whether or not the events A and C are statistically independent. So how do we do this? Well, in this case, what I'll do is I'll just clear the screen, but what I'd say here is just make sure you've got a note of parts B and parts D, just so you can see the working and what I'm going to use to answer part E. So if we just clear this dead quick. So for part E, now here, you can use your formula book. There's 3 formulas that we use to determine independence between 2 events. One of the formulas is the probability of A intersection C. So I'm using the same events here as what we're asked for. Well, this would be equal to the probability of A times the probability of C. Now we can't use this one because we haven't used, the probability of A, for example, in B or D. So we can't use this formula. But what we can use is the fact that we know if 2 events are independent, then the probability of A given C, well, that will be equal to the probability of A. Okay, so I said the probability of A, was it the probability of C? One of these, we couldn't use this formula here. We're looking to use this formula here essentially. Okay, so in that case, we know the probability of A given C. We work that out in part D. Okay, so the probability of A given C, so that was from part D. So that was from D. And we know the probability of A given C, that's equal to 7 over 30. Okay, so we just worked that out previously. And from part B now, so we need to work out, or we need the probability of A, so we got that from part B. Okay, so that was what we were looking for here, from part B. And we know the probability of A is equal to, so if you simplify this, you would get 3 over 10. So that's 3 over 10. So what we need to do is check whether these are equal in value. Okay, so if they are equal, then they're independent. If they're not equal in value, then they're not independent. So clearly 7 over 30 is not equal to 3 over 10. So in that case, A and C are not independent. So therefore, A and C are not independent. Okay. And there we have it. So that's all we needed to show really for part E. Like I said, there's this formula as well that you can use, but I think you lose the second mark here for this one if you use this formula rather than this. I think the emphasis on the mark scheme is to use this formula. But yeah, remember you can always use this formula as well, generally to check independence between 2 events. Okay, so that's part E, and now we finally arrive at the very last part here, part F. So it says, given that the integer selected is greater than 20 and prime, find the probability that it ends in a 3. So we're going to need to clear the screen just so we can finish this question. How would we do this? Well, we need to understand what the question's actually asking for here. So again, we see this word given, So we know we're going to be conditioning, and we know we're going to use conditional probability. So looking for the probability of something conditioned on something else. So what are we conditioning on here? So we're conditioning on the fact that this is going to be an integer selected that's greater than 20 and prime. So I see and, so that means we're going to have an intersection here. So we just need to find the two events here. So which event is greater than 20? Well, that's going to be the event C here. Okay, C is the event that the integer selected is greater than 20. So that's going to be C. And prime, well, we know that's the event A here. Okay, A is the event that the integer selected is prime. Okay, so we'll put our conditional probability in, so that's going to be A intersection C. Okay, that's what we're conditioning on here. And this first part here, what would this be? Well, we find that here where it says find the probability that ends in a 3. Well, the only event that's left is B. So that's going to be the probability of B given A intersection C. Now, don't overcomplicate this. Again, all we do here is just use our conditional probability formula. So in that case, this is going to be the probability of B intersection with this second part here. So that's B intersection A intersection C. I'm going to put this in a bracket here just so I don't confuse anyone. And then we divide this by what we condition on. So this is the probability of A intersection C. Okay. So this top, or the top of the fraction here, the numerator, all I've essentially got here is the probability of B intersection and then A intersection C, which would just be the same as writing this as the probability of B intersection A intersection C. Okay, so that's my numerator. And then we divide this by the probability of A intersection C. Okay, so the probability of B intersection A intersection C, so that's just where does A, B and C all meet essentially on the Venn diagram. And in that case, that would just be simply this value here. So that means we've got two values there, or two integers. And if that's a probability, that would be 2 out of 50. There's 50 possible integers, so that's going to be 2 out of 50 for the numerator. And for the denominator then, we already know that value there, the probability of A intersection C. We worked that out for another part, I can't remember which, but that was 7 over 50. Okay, and again, this cancels quite nicely here. The 50s cancel, and what I get left with is 2 over 7. Okay, so there we have it. So that's our final probability there. So that's the probability of B given A intersection C there. Okay, so that gives us the solution to question 2. Moving on to question 3 now, we have a question here for hypothesis testing with the PMCC. So 3 parts of this question, pretty standard to be honest. Part A is where we're performing the hypothesis test. So let's start with question 3, part A. So if we just read the question here and take out the important bits of information that we need. So Barbara's investigating the relationship between average income and average annual carbon dioxide emissions, CO2. Okay, so this is for different countries. She takes a random sample of 24 countries, so that's important. We'll just underline that here, 24 countries. And she finds the PMCC between the average annual CO2 emissions and average income to be 0.446. So again, we'll highlight that, we'll need that. And then in part 8, it says, stating your hypotheses clearly, test at the 5% level of significance whether or not the PMCC for all countries is greater than 0. And again, let's just highlight that here. You can also highlight the significance level if you want. We'll do that as well. So these are what I deem here to be important parts of information for this question. This part here, this 24 countries, that tells us the sample size. So we know n equals 24. This is the value that we use as our test statistic. So this is the test statistic. This is our level of significance. So we use this to find our critical value. And this helps us determine whether this is a one-tailed or a two-tailed hypothesis test. So to start with, let's give the hypotheses here. So we've got H0 and H1. So for H0 and H1, and for any hypothesis test with the PMCC, we always use the Greek letter rho. So rho, if you've not come across this before, but hopefully you have, is a slightly slanted P. It looks something like this. It don't have to be perfect, just as long as it looks something like this. And again, we use it in H1 as well. Okay, so it looks something like that. Now in H0, this will always be equal to 0. However, in H1, this can either be not equal to 0, greater than 0, or less than 0. And the way to tell is by the wording in the question in what we're asked to test. So we're told here to test at the 5% level of significance whether or not the PMCC for all countries is greater than 0. So because this is greater than 0, that means this is a one-tailed hypothesis test, and I set this being greater than 0, like that. So that gives us the hypotheses there. We know that n is equal to 24, so we use that in our formula book here to find the critical value. But first, let's just write down the test statistic, which we're given in the question. Usually to save time, you will be given this, and we're given that here, so 0.446. All we need now is a critical value to compare this to. So we're looking for the critical value, and the critical value is given by your formula book. So make sure you're familiar with how to find the critical value. You don't want to be doing an exam and not know how to find this, but it is rather straightforward. Looking at this table now, make sure you're looking at the PMCC table. Sounds kind of silly, but there's another table next to this as well for, I think it's Spearman's rank off the top of my head. So make sure you're in the correct table. Now, the level here is the significance level. And because it's a one-tailed test, we're in this column here. However, if it was a two-tailed test, you would be in this column. Remember, you divide the significance level by 2. But because it's one-tailed, we are in the 5% column. We now need to know what row we look through. So that's given by the sample size n. And we said n is 24. So we go down to 24, which is here, and we go across until we intersect with our 5% column, which is this value here of 0.3438. So 0.3438 there. And what we do here now is we compare the test statistic to the critical value, and we see whether it's greater than or less than. So because 0.446 is greater than 0.3438, in this case, we reject H0. When this is larger, or when the test statistic's larger, we reject. So we reject H0. So we reject H0, and we say there is evidence. So there is evidence at the 5% significance level. So there is evidence at the 5% significance level to suggest that the PMCC for all countries is greater than 0. You should really write that last line. I'm not going to write it just to save time because I am a slow writer, but do include that in your conclusion as well. So always make sure to give a conclusion after you accept H0 or reject H0. It's always nice to show that you understand the context behind accepting and rejecting H0. Okay, so that's all we need there for part A. Like you can see, it's usually not too many marks, 3 marks, but not too much work. So that gets us part A done. If we look at part B now, we're given a bit more information. So Barbara believes that a nonlinear model would be a better fit for the data. She uses this code in here with these variables, and she obtains this new model. And we're also told the PMCC between C and M is found to be 0.882. So we're asked to explain why this value supports Barbara's belief. So Barbara believes that a nonlinear model would be a better fit for the data. And this value here for the PMCC does actually suggest that. And the reason why is because if you notice, this is closer to 1 than this value here of this PMCC. So because 0.882 is closer to 1, what that suggests then is that there's a stronger positive correlation. So 0.882 is closer to 1, so therefore there's a stronger positive correlation. And that's all we really need to say there for part B. It is only 1 mark, so just something that's clearly pointing out that 0.882 is closer to 1, and therefore that's a stronger positive correlation. Okay, so I guess I'll mark there for part B. And then finally we arrive at part C here, where we're asked to show that the relationship between y and x can be written in this form here. So y equals ax to the power of n, where a and n are constants to be found. So pretty standard. I'll just need to clear the screen just so we can attempt this question, or this part. So part C here now. So we're asked for it in the form y equals ax to the power of n. Now to start with, we need to refer back to our model that we were given in part B. So that's c equals minus 1.82 plus 0.89 m. Okay, and she used this code in here with these variables. So m is equal to log x base 10 and c is equal to log y base 10. So I can replace c and m with log x base 10 and log y base 10. So c is equal to log y base 10, so log y base 10 is equal to minus 1.82 plus 0.89 m, where m is log x base 10, so that's 0.89 log x base 10. Okay, so that's plus 0.89 log x base 10. So what we need to do now is, if we want it in the form y equals ax to the power of n, we just need to rearrange, if we call this equation 1 here, we need to rearrange equation 1 so that y is the subject. And straight away you should see that an issue here is that we have this y as a logarithm, so this is log y base 10. So we need to get rid of the logarithms here. So the first thing we do then is essentially we're raising everything to a power of 10, so that's going to be 10 to the log y base 10, which would give us y. So we're going to get y on the left hand side once we get rid of the logarithms by raising everything to that base. And on the right hand side here then, what I'm going to get is 10. So like I said, we're now making everything as a power of 10. So this is 10 to the minus 1.82 plus 0.89 log x base 10. Okay. And from here now, this just boils down to working with your laws of logarithms. So the first thing I can see here is that because this is adding, so it's 10 to the minus 1.82 plus 0.89 log x base 10, then we can write this as a product with the same base. So what I mean by that is this would be y equals 10 to the minus 1.82, so 10 to the minus 1.82, and then we times that by 10 to the power of 0.89 log x, so log x base 10. Okay, like I said, this is just rules of logarithms and indices here. And now, because this is 10 to the power of 0.89 log x base 10, so again, we're going to cancel this logarithm here now and this power, and what I actually get then is just 0.89 x, or x I should say, to the power of 0.89, because we can use the power rule here and take that 0.89 up. So what I get here is y equals 10 to the minus 1.82, oops, get mixed up, and then we times that by 10 to the log x base 10, and then x is to the power of 0.89. Okay, so just using our rules of logarithms here, and then this 10 and this log 10 here, they cancel, just like we did with the y and this log 10 here, or log y base 10. So therefore what I get then is y equals 10 to the power of minus 1.82, so you need to put that into your calculator, but what you should find here is you get 0.015, so 0.015, and like we said, this 10 and this log x, or this log and a log base 10 and 10 here, getting a little bit tripped up, but they just cancel. And what I get left with is x to the power of 0.89. So I get x to the power 0.89 there. Okay? And like we can see, then we've actually got this in the required form, because what I've got is y equals ax to the power of m. So in that case, a is this 0.015, and my n is just simply my power. So n is equal to 0.89 there. And there we have it. So that gives us our solution to part C and to question 3 overall. Moving on to question 4 now, we have a question here on probability distributions. So to start with, in part A, we're asked to show that the value of k is equal to this value here. And k is given 5 times k over 10, k over 20, k over 30, k over 40, and finally k over 50. So how would we do something like this? Well, to be honest, part A is something that you should be familiar with how to solve. But if you haven't seen something like this before, the method and the working isn't too bad. The way to solve something like this is to be aware that these probabilities here, so these are just probabilities. So for example, 0.2, 0.2, 0.2, 0.2, and finally 0.2. And if you notice that they were all 0.2, they won't be in this case, but let's say they were, then these probabilities sum to equal 1. Okay, so what I'm saying here is the sum of these probabilities is equal to 1. So in that case, if I add each individual probability up and then set that equal to 1, then we can go on to solve for k. So therefore what we're saying here is k over 10 plus k over 20 plus k over 30 plus k over 40, and finally we arrive at k over 50, and we know this sum here is equal to 1. Okay, so what I need to do then is just simplify the left hand side and then solve for k. So if you simplify the left hand side here, whether that's by hand or by using a calculator, what you get is 137k over 600. So that's the left hand side is equal to 1. Okay, so that's 600 there. And then we just solve for k, so nice and straightforward, just times both sides by 600 and then divide by 137. And what we get is exactly what we need to show for pi a. So therefore k is equal to 600 over 137. Okay, so that's the first 2 marks in the bag. For part B here, there's a little bit more work to it, but it's nothing too tricky. So what we're given here is the random variables d1 and d2, which are independent and each have the same distribution as d. So d we're given here in pi a. And what we want to do is find the probability that d1 plus d2 is equal to 80. Give the answer to 3 significant figures. So this is just finding the probability of a sum of 2 independent random variables. Now to do this here, what I'll do is I'll just quickly clear the screen. So what we're saying here essentially for part B is if we have 2 independent distributions d1 and d2, what we're looking here, or what we're looking for here, is if I look for this value of d, little d here, so that's, it can either be 10, 20, 30, 40 or 50. What I'm saying then is this value plus, again, another value of d should equal 80. So there's only a few possible ways we can make that happen. So let's, for example, say we have d1 and we have d2 here. Okay. Well, one possible way we could do that is if d1 is equal to 30 and d2 is equal to 50. Remember, these two must sum to give you 80 here. That's what we're saying. So if d1 is 30, then d2 would be 50. That's one way we could do it. Another way we could do this is if d1 is equal to 40 and then d2 is also equal to 40. And finally, the last way we could do that is if d1 is equal to 50 and d2 is equal to 30. So d1 equals 50 and d2 equals 30. Okay, so that's the 3 possible ways of doing this. So therefore, the probability of d1 plus d2 being equal to 80, I should put that all in one bracket actually. Let's just do that again, mess that up. So like I said, these should be all in one bracket. Oops, lost that pen. So this is equal to 80, and this probability is going to be equal to the probability of d1 times the probability of d2. Okay, and that's going to be the probability of d1 equals 30 times the probability that d2 equals 50. I'll do this on the next line here. So probability of d1 equals 30 times the probability that d2 is equal to 50 plus, so this is the first one done. We now move on to the second option here. So that's going to be the probability that d1 is equal to 40 times the probability that d2 is equal to 40. So that's the second option done, and then finally we just got to do it one more time. So plus the probability that d1 is equal to 50 times the probability that d2 is equal to 30. Okay, and there we go. We've ticked off all options here. So what I need to do now is work out these individual products. So I've got the probability of d1 equals 30 times the probability of d2 equals 50. So what's the probability that d1 equals 30? Well, that's going to be k over 30. And then we times that by the probability that d2 is equal to 50. which will be k over 50. So let's go to the bottom here. So the first one here, the probability that d1 equals 30 times the probability that d2 equaling 50. Like we just said, that's going to be k over 30. So that's k over 30 times k over 50. Now we add on the probability of d1 equals 5 times the probability that d2 equals 5. And what you might see here straight away is this is going to be k over 40 times k over 40, so k squared over 40 squared. But I'll write it out in full just so we can see it. So k over 40 times k over 40. And then finally we just got to do the probability that d1 equals 50 times the probability that d2 equals 30. And essentially it's just going to be the mirror of this, so it's going to be the k over 50 times k over 30. So k over 50 times k over 30 there. Okay, so what I need to do now is just simplify this. So that's going to give me k squared over 1,500. Same here, that's going to be k squared over 1,500, and this will be k squared over 1,600. So if we just write that out again, so we've got k squared over 1,500 plus k squared over 1,600, and then finally at k squared over 1,500 again. So if we simplify this here again, whether you do that by hand or on your calculator, what you should find here is we get 47k squared. I get 47k squared over 24,000. Okay. And from here now, it's pretty simple to finish this question. All I need to do now is sub this value of k in here. Okay, so this value here for k. So even if you couldn't do part A, you can still go on to do part B as long as you understand what the question is asking for. So all I need to do now is simply substitute k equals 600 over 137 into this expression here. So that gives me 47 lots of 600 over 137 all squared, and then we divide this by 24,000. Now notice the answer should be given to 3 significant figures, this probability. So you put this into your calculator and then find that value. What you should get here to 3 significant figures is 0.0376 there. Okay? And there we have it. So that gets us the solutions part B and the 3 marks there. And then in part C here, we've got a bit of an interesting question. It's something a bit different. So what we're told here is a single observation of D is made. So the value obtained D is the common difference of an arithmetic sequence. The first 4 terms of this arithmetic sequence are the angles measured in degrees of quadrilateral Q. And what we want to do is find the exact probability that the smallest angle of Q is more than 50 degrees. So this is definitely a bit of an interesting question, and it's quite different to what you might see in your textbook. However, it's not too bad as long as you think about it in a logical sense. So for an arithmetic sequence, we always say that A is the first term. So let A be the first term. Okay, so let A be the first term. So if we think about our arithmetic sequence then, well obviously a quadrilateral has 4 angles, so we're only going to get 4 terms to this sequence. So I'm going to get A for my first term. That would be the smallest angle here. We're going to get A plus D. And the reason we know this will always be the smallest angle here is because every angle after it will have this common difference D. Okay, so I've got A plus D. The next term here is A plus 2D. And then finally I've got A plus 3D. Okay, and that's the first 4 terms, and that represents the angles of the quadrilateral Q. So we know for a quadrilateral the sum of the angles is equal to 360 degrees. So if I take these first 4 terms, add them together and set that equal to 360, so I'm going to get A plus D plus A plus 2D, and then finally plus A plus 3D. Okay, and we know this is equal to 360. Okay, so we simplify the left hand side here. I've got A plus A plus A plus A, so that gives me 4A. I've got D plus 2D, which is 3D, plus another 3D gives me 6D. So 4A plus 6D is equal to 360. And we can simplify this. If I divide the left hand side and the right hand side by 2, I get 2A plus 3D is equal to 180. Okay. Now, what we're asked for here is to find the exact probability that the smallest angle of Q, so that's the first term here, A, is more than 50 degrees. So what we require, A to be greater than 50. That's what we're looking for here. Now, we have a few possible options. We have when D equals 10, when D equals 20, when D equals 30, when D equals 40, and when D equals 50. So it makes sense to me just to start with the smallest value here and work our way up and see what happens. So let's say that D is equal to 10. So when D equals 10, what do we get? Well, we've got 2A plus 3D is equal to 180. So I've got 2A plus 3 lots of 10, because we said D is equal to 10, and this is equal to 180. So in that case, I get 2A plus 30 is equal to 180. So I get 2A equals 150. So therefore, A is going to be 75. Okay? And that would work because A is more than 50 degrees. So it works when D equals 10. So we'll give that one a tick. Let's keep moving up here now. So when we say D equals 20, so when D equals 20, what would we get here? Well, I'm going to get 2A plus 3 lots of 20 is equal to 180. And again, just solving for A here, I get 2A plus 60 is equal to 180. So therefore, 2A is equal to 120. And therefore, A will be equal to 60. Okay? And again, it works when D equals 20. So we'll give that a tick. So let's keep going here. Let's have a go now when D equals 30. So when D equals 30, what happens now? So when D equals 30, I get 2A plus 3 lots of 30 is equal to 180. So simplifying this, 2A plus 90 is equal to 180. So therefore 2A is equal to 90, and therefore A is equal to 45. However, this doesn't work because what we said here is that the smallest angle of Q, which is A, that's the smallest angle, must be more than 50. Here, we've worked out that A is 45. So we said the smallest angle is less than 50, so it doesn't work for D equals 30. And you can go on and do D equals 40 if you want, but you'll be wasting your time because if you think about this, if you start summing in larger values of D, then they will also fail as well. A will also be less than 50, so it doesn't work for these two either. Okay? So here we've got two possible options, I can't speak. We've got the probability that D equals 10 or the probability that D equals 20. These two possible options. So if we finish this off in the bottom right corner, and if I do it in a different pen colour just to make it clear. So this is all our preliminary work in here, just to want to solve this. So what this simply boils down to is this either is the probability that D equals 10 or the probability that D equals 20. Okay? So therefore, we've got K over 10, that's the probability that D equals 10. So that's K over 10. Seeing as this is OR, this is the sum of these two probabilities, so it's plus the probability that D equals 20, which is K over 20. So that's K over 20. So in that case then, simplifying this, if we put this over a common denominator, this is 2K over 20 plus K over 20, giving me 3K over 20. So I've got 3K over 20, but we know what K is. K is 600 over 137. So in that case, we can simply work out the exact value here. So that's 3 lots of 600 over 137 all over 20. And if we simplify this, making sure we give it in its exact value, its exact probability, what I get here then is 90 over 137. Okay, and that's our solution there. So make sure you give this in its exact probability. Don't write it as a decimal. Give it in its fraction form. Okay, so there we have it. So that's the solution to part C and to question 4. Finally, moving on to question 5 here. This is the last question on the stats part of the exam. And we've got a question here taking a look at quite a few different things, but essentially the normal distribution and hypothesis testing for the normal distribution. So the very first part here, part A, like we can see, it is just a 1 marker, so use this mark as a guide. Seeing as we're asked to find a probability for the normal distribution, and it's only 1 mark, we're expected to use our calculator. So let's just quickly read what we're asked to do for part A. So we're told a health centre claims that the time a doctor spends with a patient can be modelled by a normal distribution with a mean of 10 minutes and a standard deviation of 4 minutes. So we can define the distribution here. I'm going to use x as my variable. It doesn't really matter, but x is pretty standard. This follows a normal distribution with mean 10 minutes and a standard deviation of 4. So that would be 4 squared for the variance. So if we're looking for the probability that the time spent with a randomly selected patient is more than 15 minutes, we're looking for the probability that x is greater than 15. Okay. So here, just putting this into our calculator, I have a Casio graphical calculator, but I think some scientific calculators can do this as well. And hopefully you do have a calculator that can do this. It will save you a lot of time in the stats part of the exam. So when I put this in, I put this into normal CD rather than PD. Make sure it's normal CD, not PD. And you'll be asked for a few things. So you'll be asked for the data. So make sure this is a variable rather than a list. Now, because we're looking for the probability that x is greater than 15, this 15 here goes into the lower part rather than the upper part. Okay, so it's kind of the opposite. So because this is greater, you put 15 in the lower. For the upper, this needs to be an arbitrarily large value. So I just put a load of 9s in there, but just some large value. Then for sigma, that's your standard deviation. So make sure that's 4. And for mu, that's your mean. Make sure that's 10. Okay. And if you press enter, what you should get then is your probability. And what we get here to 3 significant figures is 0.106 there. Okay. So that's the probability that x is greater than 15. Like we can see, just 1 mark, we're not expecting much work. Okay. So let's have a look at part B now. This is 4 marks, and there's, definitely a bit more work to it, because now we're going to do the hypothesis test. So it says some patients complain that the mean time the doctor spends with a patient is more than 10 minutes. So the receptionist takes a random sample of 20 patients and finds that the mean time the doctor spends with a patient is 11.5 minutes. So we need to state the hypothesis clearly and use a 5% significance level to test whether or not there is evidence to support the patient's complaint. So because this is a hypothesis test, obviously it makes sense just to start by defining the hypotheses. So we're going to have H0 and H1 here. Okay. Now because we're testing a mean of a normal distribution here, obviously we're going to use mu as our parameter. So mu here and mu here. So before I put this in, for H0, this will always be equal to the value that we're going to be using, which we'll define in a moment. And for H1, well, this is dependent on whether it's a one-tailed test or a two-tailed test, and that's given in the context of the question. So if we just read the first line essentially here again, some patients complain that the mean time the doctor spends with a patient is more than 10 minutes. So that's the complaint here that we're going to be testing to, essentially deduce for this hypothesis test. So because they're saying it's more than 10 minutes, we're testing that mu is greater than 10, okay? And that means mu will be equal to 10 for H0, okay? So that's our hypothesis defined there. Now, we need to define the distribution of x bar, okay? Now, for x bar, this will also be a normal distribution. For the mean here, this just follows from what we originally had, which was a mean of 10 minutes, okay? So we use the same mean here, so that's 10. Now, be careful for the variance here. We wouldn't just write 4 squared. We need to, apply the standard error here as well. So this is going to be 4, and we divide this by the square root of n. So for this sample here, that was a sample of 20 patients, so we divide this by the square root of 20, okay? And we square all of this, because this is the variance. Now, obviously, you could write this as 16 over 20. You can do that if you prefer. It's completely up to you, but I'm just going to keep it like this for now. And now we need to test something here. So we're looking for the probability of x bar. Well, because this was a one-tailed test here, and because it's greater than, we test for being greater than here. So for a one-tailed test, what you're testing just matches what you defined in H1, nice and straightforward. So it's also going to be greater than here. And this is the evidence now. So what did we, well, not we, but what did the receptionist find? Well, she found that the mean time the doctor spends with a patient is 11.5. So X bar being greater than 11.5. Okay. So for this now, this here, we put this into our calculator again for a probability. Your mean is 10. You need to take the square root of this, obviously because this is the variance. So make sure when you put sigma in, you don't put this squared in, but just obviously the square root of this. And because this is greater than 11.5, 11.5 will go in your lower, and again, an arbitrarily large value in the upper. And if you do this correctly, what you should get here for your value or your probability is 0.046766. Okay. So that's the probability, and all we need to do now is compare this to our significance level. So we were testing at a 5% significance level, so 0.046766 is less than 0.05, that's 5%. So because it's less than 0.05, that's significant. We reject H0 here, so we reject H0. So reject H0. And we say there is evidence, so there is evidence at the 5% significance level, so at the 5% significance level, to support the patient's claim. Okay, so we always just link it back to the question and just show the examiner that we do understand the context of the question and how to link that to whether we accepted or rejected H0. So that's to support the patient's claim. I can't do English, that should be after the S, but you know what I mean. There we go. So there we go. So that's part B. So that gets us the 4 marks there, and that's all we need. So that's part B done. It's took up all the screen, so let's clear all this and have a go at part C. So in part C, we're told the health centre also claims, I can't speak, claim. So the health centre also claims that the time a dentist spends with a patient during a routine appointment, T minutes, can be modelled by the normal distribution. And this distribution is defined here. Okay, so T is a normal distribution with mean 5 and variance 3.5 squared. So using this model, part 1 here to see, we want to find the probability that a routine appointment with the dentist takes less than 2 minutes. And notice again here, just 1 mark. So we're not expecting to do this by hand, we're expected to do this using our calculator. So again, all we need to do now is just define the distribution. They've already done it for us, but I'll just write it down just so we've got it as well. So T is a normal distribution with mean 5 and variance 3.5 squared. Okay, so we're looking for the probability that T, so this is a routine appointment that takes less than 2 minutes, so we're just looking for the probability that T is less than 2. Okay, so again, put this into your calculator. Notice that T is now less than 2, so 2 will go into the upper, and it'll be minus 9999, for example, in the lower. And obviously make sure you've got mu is 5 and sigma as the square root here, or just 3.5. And in that case, if you put this into your calculator correctly, what you should get is 0.1956, and it doesn't ask for it to a certain level of accuracy, but if I give it to 3 significant figures, that's 0.196 there. Okay, so that's all we needed there for part 1 to see. Gets us the first mark. The second part here is 3 marks, and it's a little bit trickier. And notice here now, we're introducing conditional probability with a normal distribution. So we're looking for the probability that T is less than 2, given T is greater than 0. So this just links your conditional probability now. Now we did question 2 on Venn diagrams and probability. There was quite a bit there on conditional probability. And again, you can just use your formula book to memorise, or to save you memorising the conditional probability formula. In this case then, this is going to be the probability of T being less than 2, and so intersection T being greater than 0. And that'll be all over the probability of what we're conditioning on here. So that's the probability that t is greater than 0. Okay. Now, for the numerator here, you can simplify this if you just think about how this works. So the probability that t is less than 2 and t is greater than 0, well, we could just write that as the probability of it being between 0 and 2. Okay, that's essentially all that's saying there. And again, we're just over the probability that t is greater than 0. So all I need to do now is evaluate each one of these individually on my calculator using this distribution here. Okay, so obviously you should already have these into your calculator. You just need to change here. Now for this top one here, between 0 and 2, 0 is the lower, 2 is the upper. Just put that into your calculator, and what you should get for the numerator then is 0.119119, and it carries on for a little bit, but I'll just leave it there. And then we divide this by the probability that t is greater than 0. So again, just put this into your calculator. And what we get here is 0.923436, and again, so on and so on. Okay. So if we just simplify this now, what we get here is 0.129 there. Okay, giving that to 3 decimal places. That's what we're going to get there. Okay. So that's the next 3 marks. And then we arrive at the last part of C here, just asking us to explain why this normal distribution may not be a good model for t. So we just need to think about this logically and why this might not be a good model. So let's put this down here, part 3. So why might this not be a good model? Well, the issue here is that the model suggests what we'd say is non-negligible probability values for t. Essentially, t can be less than 0, which clearly doesn't make sense because t is measuring time. So if t is less than 0, we've just broke, I don't know, the universe essentially. So it doesn't really work. So in that case, what we'd say, this model suggests, so the model suggests non-negligible. I think that's how you spell it. I'm shocking at spelling. Non-negligible probability values of t. And I've run out of room, but that's the idea. So it suggests non-negligible probability values of t, which is impossible, or t being less than 0, which is impossible. Okay. Time can't be negative, essentially. So that's all you really need to say for that 1 mark. Even if you can't think of reason, it's not going to essentially define your exam. I wouldn't worry too much about questions like that, but obviously it's nice to get them. Okay, so that's part C complete, and then finally we arrive at part D here. So again, I'm just going to have to clear the screen just so we've got enough room here for part D. Just clear all that. Right, let's have a look at part D. So for part D here, it says the dentist believes that she cannot complete a routine appointment in less than 2 minutes. She suggests that the health centre should use a refined model only including values of t being greater than 2. What we want to do is find the median time for a routine appointment using this new model, giving the answer correct to 1 decimal place. So where do we begin with this? Well, it's a bit of a tricky one, and it's hard to kind of work out what we need to set up here. But the way to think about this is we're going to have to condition on something. And the thing we're going to have to condition on here is the fact that she believes it can't be completed in less than 2 minutes. So we're given, essentially it's a given that question. Okay. So what we're conditioning on here is the fact that t is greater than 2. So we're looking for the probability of something in the moment, given that t is greater than 2. Okay. Now, what we're looking for here is the median time. So remember, for the median, that's the 50th percent of the data. Essentially, it's the middle. So this probability should be equal to 0.5 if we're looking for the median. So that's going to be equal to 0.5. And essentially, what I'm looking for here now is the probability of our distribution t being greater than some value, which is the median. Okay, so this value here, let's just call it little t. This is the median. Okay. Now, it doesn't actually matter if I change this to be the distribution t being less than t it wouldn't matter because remember the median lies exactly halfway through the data if you think about it. If I do a rough sketch here, if I say that's little t there, well, this here is a probability, that would be 0.5. And again, if we do it in a different pen colour, this here, this probability will also be 0.5. Okay, so it doesn't matter if you said that was t being less than t, it wouldn't matter. I've just chose it as t being greater than little t. It doesn't really matter, but yeah, so that's why I've done it like that. Now, so like I said, this here, this is the median, so this is median. And as I said, we are conditioning on t being greater than 2 because that's what the dentist said here. So she can't, or she believes she can't complete a routine appointment in less than 2 minutes. So we need to condition on that idea. So where do we begin with this? Well, this now essentially just boils down to a conditional probability question, essentially just using the normal distribution. But if we think about it, we can simplify this a little bit. So because the dentist believes it can't be completed in less than 2 minutes, we're saying that it must be at least, or it's got to be greater than 2 minutes. So what this would be here is going to be the probability of t being greater than little t. We don't even need to think about any intersections here. And the reason why is because if we're looking strictly greater than 2, the median clearly has to be bigger than 2. Okay? So we're looking for it being greater than 2 and also greater than t. But t will always be greater than 2. So we can just define it straight away as this, as my numerator. And then for the denominator, it will be what we condition on. So that's the probability that t is greater than 2. Okay, so hopefully this part here made sense with the numerator. That's probably the trickiest, maybe the trickiest part to understand here. As long as you can get your head around that, I think we're pretty much onto it. And like we said, this is all equal to 0.5. Okay. Now, the numerator here, we can't work that out yet. But we can definitely work out the denominator here. We're looking for the probability that t is greater than 2 using this model here. Okay, that's for t. So all we need to do now is put this into our calculator with this distribution. So what I get here is the numerator, which doesn't change. So that's probably that t is greater than little t. And it's going to be all over. So the probability that t is greater than 2, if you put this into your calculator correctly, what you should get is 0.8043 and so on. And this is all equal to 0.5. Okay. Now, because I've got this denominator of 0.8043 so on, I can now get rid of this by timesing both sides of the equation by 0.8043. So I get the probability that t is greater than little t is equal to 0.5 times 0.8043 and so on. So we can simplify this right-hand side here. And what I get then is the probability that t is greater than little t. This is equal to 0.40215, and again, so on. So from here now, we can actually go on to use our calculator here. You can carry on doing this by hand, but you don't need to. You can just use your calculator from here now. And hopefully you've come across questions like this, and this is where you need to use the inverse normal function on your calculator. So if you load the inverse normal part of your calculator up, again, just like we did when calculating the probabilities, it will ask for a few things. Now, the reason we know we can use the inverse normal here is because we're looking for the probability of our distribution being greater than a value, and we know the probability. The probability here is 0.40215 and so on. So because we know that probability, we can use inverse normal. So what it's going to ask for here on the inverse normal is the data. Well, this is just a variable. We don't have a list of data, just a variable. The tail. So the tail here, what that means is essentially which way is my arrow pointing. It's a really basic way to think about it. But because it's pointing to the right here, like that, we put right as the tail. So the tail will be right rather than left. The area, that's the probability. So for that, you're going to put 0.40215 and so on. For sigma, that's just your standard deviation. So 3.5, mu, just your mean, which will be 5. And then if you press enter, you will get x inverse, which is just giving you this value here for little t. So what I get then is little t. So I get little t, which is equal to 5.8043 6, 7. That's not a recurring there. I don't like that. I'm getting rid of it. There we go. Okay, I can carry on. So I get 5.867, 25, and so on. But we only want this to one decimal place. So to one decimal place, I'm going to get 5.9 there. Okay, and that's what I get for t. So the median time for a routine appointment using this new model is 5.9 minutes there. Okay. And there we have it. So that's probably the trickiest part of question 5, part D, but we got there. So that gives us the solution there to question 5, and that brings us to the end of the stats part of the exam. So now let's move on to the mechanics part of the applied predicted paper. Starting with the very first question here now on the mechanics part of the exam, we have question 6 looking at constant acceleration. So this is a really nice introduction question here, hopefully an easy 5 marks for everyone. It's pretty brief. So what we need to do here is to read the question. So we've got a particle P which moves with constant acceleration, and we've been given the acceleration here. We know at time t equals 0, P has speed u meters per second. And at time t equals 3, so 3 seconds later, P has velocity minus 6i plus j meters per second. And what we want to do is find the value of u. So we're looking to find the initial speed here. So because we know we have constant acceleration, we can use our SUVAT equations. When we don't have constant acceleration, we can't use SUVAT, but because we know it's got constant acceleration, we're told that here, then we can use SUVAT. So I'm going to write S, U, V, A, and T. And what we need to do here now is define the letters that we know. So we don't know the displacement to do with this particle P, so we leave it S blank. U, that's what we're looking to find. We're looking to find the value of U. So I'm going to put a question mark here just to note that. V, that's our final velocity. So that's given at time t equals 3 seconds. We know that velocity for that time. So that's going to be V for us. So that's going to be minus 6i plus j. We know A, that's the constant acceleration. We're given that at the beginning of the question. So that's 2i minus 5j. And we also know the time. We're told at time t equals 3 seconds. So t equals 3. So what we need to do now is take a look at the variables, I guess if that's what we'll call it, the variables that we have, and see which of the SUVAT equations these, or which seem most appropriate to use. So, by looking at the SUVAT equations, it makes sense here to use V equals U plus AT. Okay, we've got V, we've got A, and we've got T. We want to find U. So, using this equation, we can easily find U. So, V is equal to minus 6i plus j, and that's equal to U, which we don't know, so we just put U there, plus A times T. So A is 2i minus 5j, and we times it by T, which is 3. So what I get here is 3 lots of 2i minus 5j there. Okay. So what I need to do now is simplify this bracket here, expand the bracket. So the left-hand side remains the same, minus 6i plus j, and that's going to be equal to U. So 3 times 2i gives me 6i, and 3 times minus 5j gives me minus 15j. Okay, so minus 15j. And what I want now is just the value of u, so all I do is rearrange this equation here, making u the subject. So therefore, u is going to be equal, so I need to subtract 6i off both sides of the equation. So minus 6i minus another 6i gives us minus 12i. And then we've got this minus 15j here. So what I need to do is add 15j to both sides of this equation. So j plus another 15j gives us 16j there. Okay. And there we have it. So that gives us the value of u there. Okay. So because u represents the initial speed here, that should be meters per second. Okay. And there we go. So that gets us the first 5 marks of the mechanics part of this exam and gives us the solution to question 6. Moving on to question 7 here, we have a question on forces. And this is a pretty standard type of question. It may be a little bit more complicated than this, but obviously the working here is important. What we've got is a box of mass 5 kilograms, which lies on a rough plane inclined at 30 degrees to the horizontal. Okay. The box is held in equilibrium by a horizontal force of magnitude 20 newtons, as shown in Figure 2. And the rest of it isn't too important. The only part that we need to be considering here is the fact that the box is in equilibrium and on the point of moving down the plane, with the box being modelled as a particle. Now, for part A, we're asked to find the magnitude of the normal reaction of the plane on the box. So, where do we begin with a problem like this? Well, the first thing I always like to do here is add the additional forces to the diagram. And sometimes you might not be given the diagram, you might just be given kind of the text to the question, and you need to do your own diagram. But in this case, quite nice, we've got the diagram to help us. So here, just adding on the additional forces, all I'm going to do first is just extend this 20 newtons, just so we can see a bit better what we've got here. So that's 20 newtons. We know the box has mass 5 kilograms, so it's going to be going down, and that will be 5g newtons. We know we have a normal reaction of the plane on the box, so that's going to go in out of the plane, like so. It should look a bit straighter like that, but you get the idea. That would be r newtons. And we also know the box in equilibrium and on the point of moving down the plane. So because the box is moving down the plane, friction opposes that motion. So because the box is sliding down the plane or moving down the plane, friction will be going up the plane. Okay, so it's going to look something like that. And we use mu to represent the coefficient of friction here. So it's going to be mu r n there. Okay, mu r newtons. And what we're going to need to do here to find the magnitude of the normal reaction is to resolve forces. So because I'm going to be looking to resolve forces, we need the opposite forces here, of the normal reaction. So it's going to be going down like so. And same again later on when you're finding the coefficient of friction. So we can just add that in here. Okay. So I think that should be everything we need just to get started. Obviously anything that we forgot, we can always throw back in later. So to do a problem like this, so to find the magnitude of the normal reaction, we need to resolve forces. So you need to choose the direction that you're taking as positive here. So because we're looking to find r, that's what we're asked for in part A, I'm going to resolve going out of the plane. So what I mean by that is going up towards r. So I'm resolving this way as positive. And the reason I'm choosing this way is because it keeps r as positive through my working, but it doesn't matter if you resolve the other way. All that'll happen is r will be negative. But the working, as long as you do everything correct, you will still get the same answer, like I said, assuming you do everything correct. Okay, but I'm keeping it like this just to maintain r as positive. So the issue here is these two forces of 5g newtons and 20 newtons, they don't lie on this orange line that we've drawn in. Okay, same here. So because of that fact, we need to split this into components. Okay, so splitting this into components, the first thing we can note here is this angle of 30 degrees means that this angle here will also be 30 degrees. Okay, just using properties of lines, angles, this will be 30 degrees. And same here, this angle will also be 30 degrees. Okay, so now we can split this into components by considering both forces individually. So if we start with the 5g newtons, and I'm going to use a different pen colour just to highlight this. Let's do this in red. So for the components then, if we start with the 5g newtons, what I need to do here is take this 5g newtons as being between this line and this line. Okay, essentially it's kind of like averaging it a little bit. That's how I like to think about it. It must be between these two lines though. Okay, so you need to be aware of the fact that the portion that contains the angle, this we measure as cosine. The part that excludes it, this part here, this would be sine. So in components then, I'll split this up into components. If we consider this force going down first, so this force going down first, that's going to be 5g, because this is the 5g going down, so it's going to be 5g, and because this part here contains the angle of 30 degrees, it's going to be 5g cosine 30 degrees. Okay, so if I just draw that on here, it's going to look like that. So that's 5g cosine 30 degrees. Okay, so that's going downwards. We now need this force here. Okay, so going down, or this component I should say. So for this component here, going down, then this will be 5g again, 5g, but not cosine. Like we said, this part excludes the angle, so it will be sine. So it's going to be 5g sine 30 degrees. Okay, and again, let's just add that on. So that's 5g sine 30 degrees. And again, I like to add these to my diagram. You don't have to, but I just prefer to add them on, just so I don't miss anything. Okay, so that's for the force of 5g newtons. We now need to consider the 20 newtons. And again, let's just use a different pen colour just to keep this clear. Let's do this in blue. So now we do 20 newtons, or consider the force of 20 newtons. And again, we need to average this now between these two forces. Okay, so this one here and this one here, splitting this up into components. Okay, this part here contains the angle 30 degrees, so this is the part that will contain cosine. So the part moving up, like we just said here, or the component moving up, that's going to be 20, because that's the force here, 20 cosine of 30 degrees. Okay, so like we just said, this is the force now, so it's going to be 20 cosine, because it contains the angle, and the angle is 30 degrees. So 20 cosine 30 degrees. So if we just add that on here, so that's 20 cosine of 30 degrees. I'm running out of room everywhere for all of this, but you get the idea. And then finally, we need the force going down here. Okay, so again, we've got another one going down here, or this component, I should say, really. And because this part here doesn't contain the angle, this will be 20 sine 30 degrees. Okay, and that's for the part going down. So going down. So that's going to be 20 sine 30 degrees. Okay. So essentially, we've got everything we actually need here now to go on to resolve this. Okay, we're going to use this pretty messy diagram here to get to resolving the forces. So we go back to our original pen colour, and let's take a look now at resolving the forces. So we were resolving going out of the plane as positive. So in that case, R here will be positive. So R is positive. The minus 20, so this 20 sine 30 we take as minus because it's opposite the motion we took as positive. So because we're going into the plane, that will be negative. So that's going to be minus 20 sine 30 degrees here. Okay, so we've took this as going into the plane here as negative, so this must be minus. And then same again here with the 5g cos 30. Okay, again, it's going into the plane rather than going out of the plane, so this will also be negative. So that's minus 5g cosine 30 degrees. Okay, and we know the box in equilibrium, so we know all of this will be equal to 0. Okay, now all we want here is R, so all I need to do now is just simply rearrange for R. So therefore R is going to be equal to, again, just adding this to the right hand side, adding this to the right hand side. So I'm going to get 20 sine 30 degrees plus 5g cosine of 30 degrees. Just put this into your calculator, and what you get here for R, so the magnitude of the normal reaction of the plane on the box, so R is equal to 52.4 newtons there. Okay, so that's 2 3 significant figures there. Okay, so that's for resolving forces perpendicular to the plane, and that's give us the magnitude of the normal reaction of the plane on the box. We now need to find the coefficient of friction between the box and the plane. So this is for part B. And again, we're just looking to resolve forces here. We're now going to resolve parallel to the plane. Okay. And again, we need to define the direction that we're taking as positive. So we're resolving forces here. And again, what we're looking for here is mu. So I'm going to resolve as going up the plane as positive, but it doesn't matter if you take going down the plane as positive. All that will happen is mu would be negative. But again, if all your working is correct, it will still work out correctly at the end. But I like to keep mu as positive as we're working through. So I'm resolving taking up the plane as positive. Okay. So what are we going to get here? Well, we've got pretty much everything we need here in this diagram. We know we've got mu r going up the plane. Okay. So mu r newtons going up the plane. So we've got mu r as positive because it's going up the plane. We've also got 20 cosine 30 going up the plane. We can see that here, this blue arrow. So we've got 20 cosine 30 degrees. That's moving up the plane. So again, that must be positive. But notice now, the 5g sine 30 degrees, that's going down the plane. So we take that as negative. So that's minus 5g sine 30 degrees. Okay. And again, with the box being in equilibrium, this will all be equal to 0. Okay. Now what we're looking for here simply is mu. So I need to rearrange to make mu the subject. So if I just make mu r the subject first and then divide by r, so I'm going to get mu r. I need to add 5g sine 30 to both sides and subtract 20 cosine 30 off both sides. So I'm going to get 5g sine 30 degrees minus 20 cosine 30 degrees. Okay. And like we said here, we just want mu, so we now divide by r. We know what the value of r is here. So therefore, mu is going to be equal to 5g sine 30 degrees minus 20 cos 30 degrees. And we divide all of this by r, which is 52.4. All we need to do this is put this. All we need to do now, I can't speak, is put this into our calculator. If we take g as, for example, 9.8, I can't remember what it says on the new papers to take g as, whether it's 9.8 or 9.81, but let's just take 9.8 here. For example, then what you get to three significant figures is 0.137 there. Okay, so the coefficient of friction between the box and the plane is 0.137 there. Okay, so that gives us the solution to part B and to question 7 overall. Moving on to question 8 here, we have a question on variable acceleration. So, as we've got variable acceleration, the first thing we should be aware of is that we can't use the Suvat equations. We can only use Suvat equations when we're dealing with constant acceleration. So what I'm going to do here at the very start of this question is I'm going to write S, V, and A. So S representing displacement, V representing velocity, and A representing acceleration. And we're going to need to use this for this question because if we don't have constant acceleration, we can't use the Suvat equations, so we know we're going to be using calculus throughout. And we're going to either be differentiating or integrating. And the way to remember here is if we go down, I call it a ladder. So if we go down this ladder of S, V, and A, then we differentiate. So if you've got the displacement but you want the velocity, you differentiate with respect to t. If you've got the velocity and you want the acceleration, again, you differentiate with respect to t. So this is differentiating d by dt. And if, for example, we've got the acceleration but we want the velocity, so we're going up the ladder now, then we integrate. Okay, and we integrate with respect to t. So this is going to be the integral with respect to t. Okay, and I always like to make this note here at the start of any question of this type. You don't have to. I just personally find that helps. So if you struggle to remember kind of which way you always go, I would just recommend doing something like this at the start of the question. Okay, so for part A first, let's just read the question and see what we've got. So we've got a particle P which moves on the x-axis, and at time t seconds, the velocity of P is v meters per second, and this is in the direction of x increasing. So v is given by this expression here, and we've got two intervals defined for v. So when t is between 0 and 4, then we use this expression here, and when t is greater than 4, we use this expression here. Now for part A, we're working in this interval here, so between 0 and 4, so we need to use this expression. So that's just one of the main things we need to be careful of when working through this question, that we're working with the correct expression. So for the greatest speed of p in this interval, what we need to find is the acceleration. We then need to set the acceleration equal to 0, and then we get a value for t, and that value for t will give us the greatest speed of p once we sub it back into the velocity. So, like I've just said, we need the acceleration. So we're using this expression here first. So v is equal to at minus 3 over 2 t squared. Okay, because we're in this interval here. So we now need to differentiate this with respect to t to find a, the acceleration. So a is equal to the differential of this. So this is straightforward differentiation. Differentiate at with respect to t, that would just give us a. Differentiating minus 3 over 2 t squared with respect to t, well, that's going to be 6 over 2 giving us 3, and we subtract 1 off the power, so we get minus 3t there. Okay. Now, like we said, we set a equal to 0 here. That's where the acceleration is equal to 0. So I get a minus 3t is equal to 0. So in that case, I get 3t equals 8. And all we're doing here is just solving for t. So therefore, t is equal to a over 3 there. Okay. So now that we've got this value of t, all we need to do to find the greatest speed of p is substitute this back into v here. Okay. So v, this is for the greatest speed, is equal to 8 lots of t. So if t is 8 over 3, that's 8 lots of 8 over 3 minus 3 over 2 t squared. So again, if t is 8 over 3, that's 8 over 3 squared. Okay. And just putting this into our calculator and getting the value out, what we get here is 32 over 3. Okay, so 32 over 3 meters per second. Okay, so that's our greatest speed of p in the interval from 0 to 4. Okay, so that gets us the first 4 marks there. Hopefully not too bad. Mathematically, nothing too tricky. I think it's just understanding what we're being asked for. Okay, so that's part A done. Now let's just clear the screen here, just so we've got enough room for part B. So let's have a look at part B here. So we're looking at the distance of P from O when t equals 4. So again, we need to make sure that we're working with the correct expression here. So again, we define the expression based on the interval. So because we're looking at t equals 4 here, be very careful, we're in this interval here because that includes the 4, okay, based on this inequality. So we're using v equals 8t minus 3 over 2 t squared again. Okay. Now, we've lost it here because I cleared the screen, but we had s, v, and a. To go down, we differentiate d by dt, and to go up, we integrate. So we integrate with respect to t. Now, because I've got v here, and we're talking about distance, straight away you should be thinking about displacement here. So because I've got v, and we need to go up to s now, we need to integrate. So I'm going to integrate v here with respect to t. So I integrate v dt. So that's going to be the integral of 8t minus 3 over 2 t squared with respect to t there. Okay. Well, in that case, adding 1 to the power divided by the new power, I get 4t squared there. So I get 4t squared. It would be 8 over 2 t squared. So I get 4t squared. Here now, adding 1 to the power, that would give me 3, and then we divide by that new power as well. So that's going to give me minus a half t cubed there. Okay, but again, this should be pretty straightforward year 1 integration and differentiation for part A. So hopefully nothing too tricky. Now, we don't have limits on this integral, so we should be including the constant of integration plus c. However, if you've done quite a few of these questions, you might notice straight away that for the constant of integration here, it's actually just going to be equal to 0. And the reason for that is because when I've integrated this, this is all in terms of t. There's no constants. So with t being equal to 0, p is at the origin O. What that means is s is equal to 0. So this is s, okay? But because when t equals 0, so when I substitute 0 into here, s is also equal to 0, then I just get 0 equals 0. The plus c here, okay, that we would have, will just be equal to 0. So in that case, we don't need to actually show that, but we, it is still there. I've not just kind of omitted it for no reason, okay? So that's what I get here, so therefore c equals 0, so I'll just show it anyway. So c is equal to 0. Now we're looking at the distance of P from O when t equals 4. So all I need to actually do now is just substitute t equals 4 into my expression for s, okay? So when t equals 4, we just substitute that into s here, so s is equal to 4 lots of 4 squared minus a half 4 cubed, and then our plus c was just 0. Okay, so we just need to simplify this here and evaluate this. So s is going to be equal now to, this is 64, 4 squared is 16, times by 4 we get 64. 4 cubed is 64, we divide that by 2, so that's the same as minus 64 over 2. And if we evaluate this, what we get here is 32. Okay, and we're working in meters here, so that's going to be 32 meters. Okay, so the distance of P from O when t equals 4 is 32 meters. So that's part B. So we'll just keep that up here. Part C is just literally 1 mark, nice and easy. So the time at which P is instantaneously at rest for t being greater than 4. So this is now the first time that we're working with this expression here. So if it's instantaneously at rest, what that means is that v is equal to 0. So this is why it's only 1 mark, because all I'm doing is I'm taking my expression for v here, 16 minus 2t, and I'm setting it equal to 0. We're saying that v is equal to 0. So instantaneously at rest, so that's what I mean by IAR, that tells us that v equals 0. So in that case, 16 minus 2t is equal to 0. And all I need to do now is solve for t. So I get 2t is equal to 16, dividing by 2 on both sides. I get t equals 8 there. Okay. And there we have it. So the time at which p is instantaneously at rest, that would be 8 seconds there. Okay, so that's part C, just 1 mark. And then we arrive at part D, where we can see there's a lot of marks, 8 marks for this final part of the question. And the thing with this part here, part D, is parts B and C are designed to help us answer for part D. Okay, so make sure you've got a note of what you got in C and part B here, because we will need them for part D. So I'm going to clear the screen now. Let's have a go at part D. So where do we begin with part D? Well, we're looking for the distance, or the total distance travelled by P in the first 10 seconds of its motion. Now, because we're using variable acceleration here, and we've got this defined over 2 intervals, so between 0 and 4, we have this velocity here, 8t minus 3 over 2 t squared, and then when t is greater than 4, we have 16 minus 2t. I'm going to split this up now into a few parts. So part B helps us because we already know the distance for the first 4 seconds. When t equals 4, we know the first 4 seconds worth of the distance travelled. And then we need to consider what happens when t is greater than 4. Okay, so let's just remember what we did first. So we know it was 32 meters in the first 4 seconds. So in the first 4 seconds. And we got that from part B. Okay, so that's from part B. So you don't need to recalculate that. We can just note that here. Okay. So because we're using V here, for t being greater than 4, and we're looking at, again, distance, you should be thinking now that we need s. Okay, so we need to integrate again here. So we need to integrate v with respect to t. So we now integrate 16 minus 2t with respect to t. So here I would get 16t. So this is s, so s is equal to 16t. I would then get minus 2t squared over 2. So that would give me minus t squared. minus t squared. And again, we do need the constant of integration here because we have no limits. That's going to be plus c there. Now, be careful with this one because c won't be equal to 0 in this case. And the reason why is because we know there was 32 meters traveled in the first 4 seconds. So that's going to be kind of essentially our initial conditions here, because we're saying when t equals 4, s is equal to 32. Okay, so I can now substitute this back into here and solve for c. So s is 32 and t is equal to 4, so that's 16 lots of 4 minus 4 squared plus c. Okay, so we now need to solve for c here. Again, just put all this into your calculator, you don't need to do this by hand, but what you should get here is that c is equal to minus 16. Okay, so in that case, s is equal to 16t, so essentially I'm just writing this out again, but with c here, so 16t minus t squared minus 16. Okay, so now we need to consider what happens for the next essentially 6 seconds from being greater than 4 all the way up to 10. Okay, so we're looking for the first 10 seconds of its motion. And this is where it gets a little bit tricky, and we also need to consider what happens, or what we found in part C here. Okay, so let's just work up to 8 for now. So we're going from t equals 4 up to 8. So from t equals 4 to t equals 8. And the reason why I'm only going up to 8 rather than 10 here is because something happens at 8. Okay, and if you refer back to what we found in part C, we found the time at which p is instantaneously at rest was when t equals 8. Okay, so let's just go up to t equals 8 for now. So what we need to do here is take our displacement here, s, we need to substitute 8 in, and then we substitute, subtract, sorry, I can't speak, what we got for t equals 4 here, which we already know was 32. Okay, we're going to subtract that off, and that would give us the distance travelled between 4 and 8 seconds, and then we're going to do that again for 8 to 10 seconds. Okay, so essentially I'm just splitting this distance travelled into 3 parts, from 0 to 4, 4 to 8, and then 8 to 10. Okay, so we already know 0 to 4, we're now calculating 4 to 8. So when t is equal to 8, so when t equals 8, we know s is equal to 16 lots of 8. So 16 times 8 minus 8 squared, and then we minus the 16. So just using s here, so minus 16. And again, just put this into your calculator, and what you should get here when t equals 8 is we get 48. Okay. Now I want to subtract, I keep wanting to say substitute for some reason, I want to subtract here this lower bound when t equals 4 off. Okay, and that would just give me exclusively the distance between 4 and 8. So in that case, from 4 to 8, that's going to be, so if I just do it in a different pen color just to make it clear, so from 4 to 8, that's going to be equal to 48 minus when t equals 4, which was 32. So 48 minus 32, in that case we get 16. Okay, so that's 16 meters. So between 4 and 8 seconds, it travels 16 meters. So all we've got to consider now is what happens between 8 and 10 seconds. And if I just draw a quick sketch of why this is a bit of a tricky question, or why it's a slightly tricky question, is because the motion looks something like this. So if I just draw it, so let's just say here and here, this is where it would be t equals 8 there. Okay, so this second dotted line here, this would be where t equals 8. The motion, it goes back on itself. Okay, the direction changes, and this is because it's when p is instantaneously at rest. That's when t equals 8. So essentially what happens here is it goes backwards. Okay, so what we've worked out here, this part, this will be 44 meters. Okay, that's going to be 44 meters. What we need to do now is just consider this final part here. So this is from 8 to 10 essentially. Okay, so I'm running out of room a little bit. Have we got enough room over here? Let's try it. So we now just need to consider from 8 to 10. So from 8 to 10. So from 8 to 10. All I need to do now is substitute 10 in to S. So when t equals 10. And again, I just want to make clear this diagram is not perfect, but just to give you a bit of an idea of what's actually happening. The direction is just changing with the particle here. So when t equals 10, we get S equals 16 lots of 10 minus 10 squared and then minus 16. Okay, put that into your calculator, and what you should get there for when t equals 10 is 44. Okay, so we've got to be careful here, because what we wanted to do now is do it from 8 to 10. So again, we subtract the lower part off here, which is when t equals 8, which we know is 48. Okay, so we do 44 minus 48, so 44 minus 48, and this gives us minus 4. Okay, and this minus part is because, like we said, the direction is reversed here. Okay, so this is going to be 4 meters essentially there. So in total then, what we can see here is we've travelled 44 meters. It's then travelled another 4 meters and then gone back again on itself for another 4 meters. So all we need to do then is essentially just tally all of this up. So the 3 parts that I've broken this up into then was from, so if I just use another different pen clear just to make it clear, because it's getting pretty messy. So from 0 to 4, we worked that out as 32 meters. Okay, so that was 32 meters. Then from 4 to 8, we got, what did we get? We got 16. We got that there. I'm going to say I'm getting tripped up, but there's that much right on the screen. 16 meters there. And then finally, what we got here was minus 4. But obviously, we're going to take that as positive, because all this is telling us it's just the direction is reversed, but it's still 4 units. Okay, so from 8 to 10, that was 4 meters. Okay, so all we need to do then is add all of this up. This would give us the total distance travelled. So the total distance is equal to 32 plus 16 plus 4. So 16 plus 4 is 20, plus the 32 gives us 52 meters there. Okay, so the total distance travelled by P in the first 10 seconds of its motion is 52 meters. Okay, so hopefully my explanation made sense. There's a lot of work on the screen and it is pretty messy. But like I said, I've broken this down into 3 different parts. So from 0 to 4, which we did in part B. Then I did from 4 to 8, and then because at 8, it's instantaneously at rest, and the direction changes. I've then done from 8 to 10. Okay, so from 8 to 10, it travelled 4 meters further. So, like I said, definitely not an easy part. That part D is a little bit tricky, but hopefully that just about made sense. So there we have it. So that gives us the solution there to question 8. Moving on to question 9 now, we have a question here on projectiles. And what we've got is a ball that's thrown from a point O, like we can see on the diagram here, which is 6 meters above horizontal ground. The ball is projected with speed u meters per second at an angle theta above the horizontal. There's a thin vertical post which is 4 meters high and 8 meters horizontally away from the vertical through O. And what we're told here is the ball passes just above the top of the post 2 seconds after projection. So what we're saying here is this is t equals 2 there. And the ball is modelled as a particle. So for part A, we want to show that tan theta is equal to 2.2, and part B is just 2 marks after that, which kind of goes hand in hand with part A. Okay, so essentially we're going to answer A and B almost together. So if we start with part A, what we want to do is show that tan theta is equal to 2.2. So what I need to do here to start with is to take this initial velocity u meters per second, and I need to split this into components. So I'm going to get two components. I'm going to get my horizontal component. That's going to look, say, like that. And I'm going to get my vertical component. And that's going to look something like that. So, given that the horizontal component contains the angle here, theta, that would be in terms of cosine, like we've discussed on the previous question. If the component contains the angle, then it's going to be cosine. So this component here, the horizontal component, that will be u, the initial velocity here, so u, cosine because it contains the angle, so u cos, and then the angle itself, theta. So we get u cos theta, and then clearly the vertical component will just be u sine theta. Okay, so that's the components defined there. So where can we begin here? Well, what we need to do is consider both the horizontal motion and the vertical motion. Doesn't matter which one you start with, but to me it's easier just to start with the horizontal motion here. So if we start by considering the horizontal motion, well, we know the velocity will remain constant here. Essentially the ball is modelled as a particle, and in that case the effect here will be under gravity, so the acceleration will be constant. Okay, so a meters per second. Okay, so as the velocity remains constant, in that case then, if we do the distance, so we know the distance here is 8 meters, and then we set that equal to speed times by time, then we can set up an equation here. So what do we mean by that? Well, we know the distance is 8 meters, so we know this is 8. We know this will be equal to the speed multiplied by the time. So the speed is our horizontal component here, u cos theta. So we've got u cos theta, and then we times this by the time, which we know is when t is equal to 2. So we times this by 2. Okay. So here, what I'm going to do is I'm going to divide both sides of my equation by 2. So I get u cos theta is equal to 4. Okay. Now, because the horizontal motion can only go in this direction, we didn't need to define a positive sense. However, for the vertical component, we do need to define our sense of which way is positive. So, given that the projection is going up initially, I'm going to define my vertical motion as being positive going up. Okay, and I'm going to do that throughout question 9 here. So, for the vertical motion, I'm taking upwards as being positive. Okay, so like we said before, we have constant acceleration here. The acceleration doesn't change, so we can use suvat. So we need to use suvat here. So we're using suvat. Okay, so what I'm going to do is I'm going to write down my letters S, U, V, A, and T. Okay. So what do we know here? Well, let's start with S here, the displacement. Well, we start at this point, we are projected upwards, and then at this point here, what would be the height? Well, we've gone from 6 down to 4, so that's a displacement of -2, okay, because we've gone down. Well, we're taking up as being positive, so this would be -2, okay. The initial velocity for the vertical component, that's easy to see. That'll just be u sine theta. So we get u sine theta. Okay. V, we don't know what that is. So we just leave that blank. We can't put anything for that. For the acceleration A here, well, as acceleration is due to gravity, in that case it's going down, or downwards we should say, and we took upwards as being positive, and this would be -9.8. Okay, that's -9.8, and t we know is 2 seconds, so that's going to be t equals 2. So what I need to do now is find the suvat equation that links all of these letters together. Okay, so what you should find here is the equation that we're going to use. So we're going to use S equals ut plus a half at squared there. Okay, so in that case, all I need to do now is just simply substitute everything that we know here S, U, A, and T into this equation. So S is minus 2. I'll do this in a different pen colour. So S is equal to minus 2. This is equal to U times T. So U is U sine theta times by T. So I'm going to get 2 lots of this. So I get 2 lots of U sine theta plus a half A T squared. So A is minus 9.8. So that's minus 9.8. And T is 2. So if we square that, we get 4. Okay, so times by 4. And it's just a matter of simplifying here. Well, given that I've got a half times minus 9.8 times 4, a half of 4 would be 2. And what I noticed then is I've got minus 2 is equal to 2 lots of U sine theta plus 2 lots of minus 9.8. So because I've got a minus 2 here, I've got a 2 here and a 2 here, I'm just going to divide through both sides here by 2. Okay, so in that case, dividing across by 2, I get minus 1 is equal to U sine theta, and this would be just minus 9.8, so minus 9.8. And in that case, if we make U sine theta the subject here, then what I get is U sine theta is equal to 8.8. Okay, so U sine theta is equal to 8.8. Now, what we're looking to show here is that tan theta is equal to 2.2. So we somehow need to link now U cos theta equals 4, U sine theta equals 8.8 to give tan theta is equal to 2.2. And hopefully you can spot straight away that we need to make use of our trigonometric identities here. Well, in this case, if we take U sine theta equals 8.8 and we divide it by U cos theta equals 4, then that will give us tan theta, okay, using our trig identities. So if we call this equation 1, call this equation 2, then I'm going to do equation 1 divided by equation 2. Okay, so if we just finish this off up here, where's my pen gone? There it is. So I've got U sine theta all over, what do we have? U cos theta even. So U cos theta. And we know U cos theta was equal to 4. So that's going to be a denominator of 4. U sine theta is equal to 8.8. So what I get then is the U's cancel. Sine theta over cos theta, nice and straightforward, just gives us tan theta. So we get tan theta on the left-hand side. And then 8.8 divided by 4, that gives us 2.2. Okay, so tan theta is equal to 2.2 as required. Okay, so there we go. So that gets us the first 5 marks there, showing that tan theta is equal to 2.2. We now move on to part B, which even if you can't do part A, you can still attempt part B without a solution to part A. And the reason for that is because they've given you that tan theta is equal to 2.2. Okay, if we weren't given this, then you wouldn't be able to answer part B, but because we know this, we can go on to attempt part B. So why can we attempt this? Well, the reason why is because I just need to work out what theta is. Okay, if we can work out what theta is, we can then simply just rearrange, say, equation 1 or equation 2 in terms of U and substitute our value of theta in. Okay, so it's rather straightforward. What I'm going to do is I'm just going to clear the screen just so we've definitely got enough room for this. Go back to our original pen colour as well. So for part B here, like I said, we're just going to rearrange equation 1 or equation 2, but first we need to find theta. So theta here will be equal to tan inverse on both sides. So that gives me theta on the left-hand side, and that's going to be equal to tan inverse of 2.2. Okay, all you need to do, put this into your calculator. What you get here for theta is we get 65.556 degrees. So, like we said, now we can rearrange one of the equations that we originally had for U. Okay, so I'm going to rearrange this, making this be U is equal to 4 over cos theta. Okay, but we know theta is 65.556. So all I need to do now is just replace theta with this value. So u is going to be equal to 4 all over cosine of 65.556 degrees. Okay, and if I input this into my calculator now, what I get here is 9.666, so on and so on. But if we give this to a sensible degree of accuracy, say 2 significant figures, then I'm going to get 9.7 there. Okay, and this is the initial velocity, so that's going to be meters per second. Okay, so there we have it. So that gives us the solution there to part B for the value of u. Now for part C, we're told the ball hits the ground t seconds after projection. We need to find the value of t. So in this case, what we need to do here is consider the vertical motion. So what I'm just going to do before we start this is just clear the screen, just so we've got enough room. So we need to consider the vertical motion. Again, because it's projected initially upwards, I'm going to take upwards as being positive here. So considering the vertical motion, consider the vertical motion. Again, like I said, I'm taking upwards as being positive here. Well, again, in this case now, we just simply need to apply suvat. We know this would be at this point here, t. This is where it hits the ground. So, what can we say here? Well, we know the displacement, so we're going to set up our suvat values. So suvat. So we know the displacement has gone from here all the way to here, okay? So in that case, the displacement, if we're taking upwards as being positive, the displacement will be minus 6, okay? So S is equal to minus 6. Now for u, that's the vertical component here, which we worked out before, was u sine theta. But in that case, like we worked out before, the initial finger here was 8.8. Okay, so this is going to be 8.8. I forgot to actually update my diagram before, but I would recommend updating the diagram as you go. So this is 8.8, and it was 4 across 4 meters per second there. Okay, so I get 8.8 there. The final velocity we don't know. Because, well, be careful here, this isn't going to be 0. It's just before it hits the ground, so we don't actually know that. So again, we just need to leave that blank. A here, again, this is under the effects of gravity, so we have constant acceleration, and that value there will be g, which we're going to take as minus 9.8. Remember, we took upwards as being positive, gravity coming downwards, so minus 9.8 there. And finally, the time here, t, well, we've just said that's big T. Well, that's what we're asked to find, big T. So we put T in there. And again, we just need to find an equation now that links all of these together. And again, I'm going to make use of S equals UT plus a half AT squared. Okay? Again, all I need to do now is simply substitute all my values here for S, U, A, and T into this expression, or this equation. So S is equal to minus 6. I get minus 6. UT, so U is 8.8, times that by T here. So I get 8.8 T plus a half of AT squared. So A is minus 9.8, and we divide that by 2. So that would give me minus 4.9. So I get, well, let's just write it in full. I get half of A minus 9.8, and then we times it by T squared. Okay, but like I said, this will be minus 4.9 in a moment. So we'll just, again, simplify what we've got. I get minus 6 is equal to 8.8 T, and I get minus 4.9 T squared. Okay, so what can we do here? Well, notice we've got this quadratic equation here. So what I want to do is set this equal to 0 and go on to solve this. So making this T squared positive, so taking this and this to this side, I'm going to get 4.9 T squared minus 8.8 t, and then I've got minus 6, and this is all equal to 0. Now it's up to you whether you use the quadratic formula here. I would just recommend using your calculator. You know, if you've got the quadratic, or you can input polynomials into your calculator and it'll give you the solutions. I've just done that here. And using my calculator, what I get then, my positive solution, is that t is equal to 2.32. Okay, so this is 2.32 seconds. Okay. And there we have it. So that's the solution to part C. And then finally, we arrive at D here. So for D, we're told that immediately before the ball hits the ground, the direction and motion of the ball makes an angle alpha with the horizontal. Find alpha. So what I'm going to do is I'm just going to clear this little drawing that I've done for T, this little T here and this point, and just think about what's happening here. So immediately before the ball hits the ground with the Immediately before the ball hits the ground, the direction of motion of the ball makes an angle alpha with the horizontal. So the way to think about this is it's essentially carrying on. Obviously, it doesn't carry on through the ground. But what I'm looking for here is this angle alpha. That's what I'm looking for here. Okay. So how do we do this? Again, I need to consider vertical motion. So we consider vertical motion. Consider vertical motion. Again, because we initially project upwards, I'm taking upwards as being positive. So in that case, applying that again here. So S, I don't have much room, U, V, A, and T. And the reason why I'm doing this is because we need the components. So what I need here is this component and this component. The reason why I'm splitting this into components is because I want to make a triangle here. And with that triangle, we can then easily apply trigonometry and find that angle alpha. So what am I going to get here? Well, we know the horizontal component here, based on this horizontal component, will be the same. So this will also be 4 meters per second. Okay, so what we need to do then is find this one. Well, S here will also be minus 6. So S is minus 6. U again, just like we got here, will be 8.8. V, again, we don't know that. A, again, using the fact that it's under gravity, that will be minus 9.8. And then finally, T will be the time here where it hits the ground, which we've just found in part C. So you can either input that as 2.32 or just write big T if you prefer, but we'll give it as 2.32 there. Okay. So now we've got everything we need. We just need to use an equation here to find what we need. Now, it's up to you which equation you use. What we're looking for here is V. So there's quite a few different options you can use here. The simplest one I think to use here is V equals U plus AT, but there is a number of different options here, so feel free to use whichever you prefer. So in that case, V we don't know, that's what we're looking to find, is equal to U, which is 8.8, plus AT. So A is minus 9.8, so that's plus minus 9.8, times it by T, which is 2.323, and so on. Do try and use as much accuracy as you can here for the value of T. 3, 2, 3, and so on. And if we evaluate this, what we get for V here is minus 13.965, and so on. And it's no surprise that V is negative here, given that V is opposing the motion that we took as positive. We took upwards as positive, given that this is going down. That makes sense that we get a negative answer. Okay. So what I've got then is a triangle, a right angle triangle. Doesn't matter how you draw the triangle, just as long as you label the sides correctly. And I'm shocking at drawing triangles, so I get something that looks like this. That would be my right angle there. This would be my angle here, alpha, that I'm looking for. So that's alpha. Well, this is my horizontal component, so that would be 4. And this one here is the vertical component that we just found, which is the 13.9654. Okay, so in that case, if I want alpha, this is just simply an application now of basic trigonometry. I've got my opposite, I've got my adjacent, so this is going to be tan that we're using. So therefore, alpha is equal to tan inverse. So it's tan inverse of the opposite over the adjacent. So opposite over the adjacent. So 13.9654 all over 4 there. Okay. And what you need to do here is just put this tan inverse of this expression into your calculator. And what you get for alpha is you get 74 degrees there. Okay, so I've rounded that to 2 significant figures. And there we have it. So that's our value for alpha. That gives us the solution to part D and to question 9 overall. And finally, we arrive at question 10, which brings us to the end of this predicted paper. Now, this question's a little bit shorter than I really wanted it to be, but I am running over quite a bit here, and you know, this brings the marks perfectly to 50. So I thought I'd kind of just shorten this one a little bit, but hopefully it still gives a bit of a challenge, you know, to conclude the paper. So, question 10. So there's a lot of text here, and in the very first part, we just asked to show that the tension in the rope is equal to this expression, which looks pretty horrific, and there is only 3 marks for this. So in terms of the actual work, we're getting into some of the trickier stuff here for not really as many marks as what we saw at the very beginning of this paper. However, we can still get these marks. So where did we begin with a question like this? Well, I'll give you a moment just to read everything here, just so you can take in what we've actually got. But with a question like this, we always need to add on the forces ourselves. So, looking at this diagram here, figure 3, what can I add on? Well, we know we have a plank AB here. That's modelled as a uniform rod. So because it's a uniform rod, that means the mass will be exactly halfway along the rod. So if this total length here is 2A, then this would be at, say, here A. Okay. And because it's got mass M, this force here will be mg. Okay. What else do we have here in our diagram? Well, we're also going to have a tension force in the rope. Okay, and it's going to act up like this. Okay, so we're going to add that in, say there. We'll call that T for tension. We also have a small block of mass 3m, and that's at this point here P, which is modelled as a particle. So we can also add this force on. That will be 3mg. Okay. And what I'm also going to do here now is split my tension up here into components. So I'm going to have a vertical component looking something like that. I'll also have a horizontal component looking something like that. So we have to decide how we label these components now. Well, the part that contains the angle here, alpha, is the horizontal component. So we'd write that as T. So it's going to be T. Because it contains the angle, it'd be cosine. So it's T cos, and then the angle. So it's alpha. So it's T cos alpha. And then clearly the vertical component will be T sine alpha. Okay, so T sine alpha for the vertical component. And I think that's pretty much everything. You know, it is also worth mentioning here that there's going to be a reaction force at this point here. This rod would want to slide down this, is it a wall? This wall here, yeah, so this wall here. The plank would want to slide down this, so there's a reaction force. And when these two meet, we get this reaction force that may go, say, up like this. Okay, and we'd call this R. Okay. And I think that gives us everything we need now to tackle part A. So what we want to do is show that the tension in the rope is 5mg times 3x plus a all over 6a. Okay, so that looks pretty grim. How do we get to this expression? Well, to do this, what we need to do here is take moments. Okay, so we've got to decide where we take moments about. Now, I'm going to take moments here about A. And the reason why I'm taking moments about A is because we have this force here, R. But remember, if you take moments about A, this ignores R. And because we have no information about R, it makes sense to take moments at A. So in that case, what we're going to do is take moments about A. So for part A, take moments. So we take moments about A. Okay. So if we take moments about A, we also need to define a sense of, which direction will be positive. So when we say that, we say either clockwise is going to be positive or anti-clockwise, counterclockwise. So in that sense, I'm going to take moments about A, and I'm going to take anti-clockwise as being positive. It doesn't actually matter which way you go here. It's completely up to you. It's not wrong if you say clockwise is positive. You should get the same answer as long as you do all the maths correct as well. Okay. So, taking moments about A then, what we need to do now is consider each individual force here and the distance taking us to A. Okay. So, if we've got this force here, T sine alpha, well, from T sine alpha all the way to A, we know that length there is 2A. I've kind of drawn over it, but the length here from A to B is 2A. Okay, so it's the force times by the distance. So the first part here will be, we also need to consider whether it's going to be positive or negative. So the way I like to think about this is, imagine I'm kind of holding this rod up at this point here, A. Well, the force is acting upwards. So if I have my finger here and I pushed upwards, imagine this is just a ruler. Well, the ruler would go in this direction. It would go around, which is the direction we've assigned as positive. So in that case, this would be positive. So it's going to be T sine alpha. So T sine alpha times by the full length, which is 2A. So T sine alpha times 2A. Okay, so that's the first force there. The T cosine alpha we don't need to include. So we move on to the next force here. So we've got 3mg. So 3mg is my force. And if you think about this now, if I've got my finger here holding this kind of ruler up, and the force is acting downwards, so I push down on the ruler, well, the ruler would go counterclockwise in that sense then. Okay, so because I said it would go clockwise and I said anti-clockwise is positive, then this will be negative. So this is going to be minus 3mg, so 3mg, and then we times that by the distance. And the distance here from P to A is this length here, x. So it's 3mg times by x. Okay, and then finally the only other force left here then is this force here, mg. Well, for mg, again, the force is acting downwards. So if my finger's here and I push downwards, this would go clockwise, and in that case it must be negative. We've said anti-clockwise is positive, so this will also be a minus. We take the force, mg, so mg, and we times it by the distance. So because this was the centre of the rod, so that would be A. From here to here, that would be a length of A. Okay. So we just note that there. So that's going to be mg times by A. Okay. So up to now, everything is looking good. We just need to start cleaning this up. The first thing to note here, though, is we have this T sine alpha. So we need to deal with this sine alpha here. Now, because I know that tan alpha is 3/4, so tan alpha is 3/4, then we also need to find expressions for sine alpha, and we'll do cos alpha just in case we also need it, but we definitely need sine alpha here. Okay, so if I've got tan alpha is equal to 3/4, by basic trigonometry, this would just be a right angled triangle. And for tangent, that's opposite over adjacent. So the opposite here must be 3. So if this is my angle, this is 3. And my adjacent here would be 4. Okay. And by Pythagoras, this length here will be 5. Okay, it's a basic 3, 4, 5 triangle. So in that case, if I want sine alpha, then in that case, that's going to be opposite over hypotenuse. So opposite is 3 over the hypotenuse, which is 5. So I get 3/5. And like I said, let's just do cosine alpha while we're here as well, just in case we do need it. So cosine alpha, that is equal to adjacent over hypotenuse, so 4/5. Okay, so 4/5. So that gives us everything we should need now. Again, if we just clean this up, if I just get rid of my triangle, just so we've got enough room. Get rid of this here. So in that case then, t sine alpha, well that's going to be, so if we just do it down here, so that's going to be t lots of sine alpha, which is 3/5. So that gives me t lots of 3/5. And then we times that by 2a. So times that by 2a. I've now got minus 3mg times x. So minus 3mg times x. Again, I'm just going to keep these in brackets here just so I can keep this clean. And I've got minus mg times a. So minus mg times a. Now, here, because this is in equilibrium, this will all be equal to 0. So I can set this equal to 0. And what I want to do now is start rearranging this. So I've kept these as they are for now, because what I'm going to do in a moment is factor out the mg. Okay. So if we take this across, I get t lots of 3/5 times 2a. And that will be equal to positive 3mg times x plus mg times a. Okay. So what we're going to do here now is start factoring out. So I'm going to factor out the mg. So I'm going to get mg, and then in a bracket I'm going to get a plus 3x. Okay. So we took that onto the other side. So from here now, it's just a matter of cleaning this up. Remember, we want T, the tension. So we need to start simplifying this. Now, because I see in this expression it's 5mg, I'm going to times across here by this denominator of 5. So that gives me T times 2, 3 lots of 2a, so that'll give me 6a. I nearly missed the 3 then. We've still got that 3 here, and I've times across by 5. So I get 5mg times a plus 3x. Okay. And therefore, we just want t, and notice if we just divide by the 6a, we get exactly what we needed here. So therefore, t is equal to 5mg times a plus 3x all over 6a. Okay. And there we have it. So that gives us the tension in the rope being this expression here that we needed to show. Like you can see, for 3 marks, this is a lot of work, especially when we compare it to some of the earlier questions on the mechanics part. But hopefully that does make sense what we did there. Okay, so that's part A. And then for part B is a bit shorter, quite nice. So if we just clear all this, for part B then, it says the magnitude of the horizontal component of the force exerted on the plank at A by the wall is 2mg. So what that's telling us here is there's a horizontal component of this force acting in this direction, and we know the magnitude of that force, that's 2mg. Okay, so that's 2mg. And I've took them off here, but we did have our components. We had the tension, T, and then we had T sine alpha, and we had our horizontal component of T cos alpha. Okay. Now here, what I need to do is resolve forces. Okay. In that case, if I resolve, so this is for part B, if I resolve and I take positive as being in this direction, okay, then what I'm going to get is 2mg will be positive, because that's going in that direction. So this would be 2mg. However, the only other force that's opposing this is T cosine alpha. Okay, but because that's going in the opposite direction, that will be negative. So that's going to be minus T cos alpha. And again, because the rod is in equilibrium, or because it's in equilibrium, the plank, I can't speak, then this will be equal to 0. Okay. So we're getting there now. All I'm going to do is basically substitute what we know. Okay, so we got t cosine alpha before, so we did need it, so that was quite handy. What I'm going to do first is say 2mg is equal to t cosine alpha. Okay, and from here now, like I said, we know what cosine alpha is. So cosine alpha, if we just write that down again, because we do need it. So cosine alpha, that's equal to 4/5. Okay, so we've got 2mg. So we've got 2mg is equal to t cosine alpha, where cosine alpha is 4/5. So I get 4/5 of t. Okay, but we know that the tension T is equal to this. So even if you couldn't show this in part A, you can still attempt part B, okay, because we know what the tension is. So it's going to be a bit messy, but I now need to replace T with this expression here. So if I just keep it so T's on the left-hand side, I'm going to get 5mg times 3x plus A all over 6a. That's going to be equal, sorry, I need to times that by 4/5, and that's equal to 2mg. Okay, so yeah, it's definitely not nice. Obviously, just times in these two fractions together, I'm going to get 20mg, 20mg times 3x plus a. And that's going to be all over 6a times 5, which gives me 30a. Okay, and that's equal to 2mg. And we can start simplifying here. I can divide top and bottom of the left-hand side by 10. So that's going to be 2mg over 3a here. So 2mg times 3x plus a all over 3a. And because I've got a 2mg on both sides, we can also divide by 2mg. So I divide by 2mg, that would give me 1 there. Again, divide by 2mg, that will also give me 1. So what I've got here now is, I've run out of room a little bit. Let's clear the screen. So clear the screen. So what I've got then is a plus 3x all over 3a is equal to 1. Now we want x in terms of a, so that means we're making x the subject. So I'm going to times by 3a, so I get a plus 3x is equal to 3a. Again, we're making x a subject, so subtract a off both sides. So 3x is equal to 2a, and therefore x is going to be equal to 2a divided by 3. So 2a over 3 there. And there we have it. So that's x in terms of a, and that gets us the final 2 marks there. Okay. And there we have it. So that gives us the solution to question 10 and brings us to the end of the mechanics part and the end of this predicted paper. Like I said, I wanted question 10 to be a little bit longer, but the timing has been not the best by me on this exam. Hopefully you'll finish it in a bit better time than I did. However, I hope you have found this helpful. And like always, any issues, if I have made a mistake, there's a good chance because I am shocking at mechanics. Please just leave a comment down below. Feel free to help each other, and best of luck for your exam. Cheers.